The x-axis is surface temperature, and the y-axis is luminosity. The main sequence is about stars' life cycle. Stars spend most of their lives on this sequence. There's nuclear fusion that happens where they fuse hydrogen into helium, creating energy and shining brightly. The star size and color on the main sequence depends on its mass. The bigger the star, the brighter and hotter it will be. But the stars will die quickly because they run out of hydrogen fuel faster. A sun-like star begins its life as a cloud. It's made of gas and dust. It's called nebula. After a nebula becomes a less massive star, it enters into the main sequence. It's the longest phase for a sun-like star. When the star burns out hydrogen in the core, it will be replaced by helium. Then the star becomes red giant. Planetary nebula is after red giant phase. It will cause explosion of the star. There's no nuclear fusion during what phase. So the star's light turns weaker and it becomes blue. A nebula can become a massive star and then red supergiant. Supernova will explode after the red supergiant phase, and the substance will either become a black hole or nitrogen star.
I don't understand why the bigger the star, the brighter and hotter it will be. I don't know why.
I think it's because of the mass.
The star's mass? Why is that?
不好意思，你有提到那个，就是它是 star size 跟温度的关系。我的问题是，就是它那个 HR diagram 其实没有特别提到 star size 直接的关系吧？我在问他有没有解答到这部分。
In the HR diagram, the inventors, they did not really talk about star size. So how do you know from the HR diagram that, because you often see HR diagram with size of the star. So how do they know that?
I don't know.
What is surface temperature? It's not like they use a thermometer to measure its temperature. Of course not.
他说研究热辐射光谱的时候，发现了在一个单位面积它们有关联。
Surface temperature is actually related to the Fraunhofer spectra when we talk about redshift. And how do they know luminosity?
标准烛光吗？
I think we talk about the Cepheids, and by studying it, we know that there are luminosity depending on the frequencies. They are varying in luminosity, and then we can use a formula that use the distance to find the distance and the true luminosity.
What Aso said exactly what I wish to know from you. You measure brightness. That's how bright the star is from the perspective of an observer. And then with some other approach like parallax, you can know, or standard candles, you can know the distance. Then at the end, you know the luminosity. That's how we know it. Tiffany, thank you. I want to say one word about the presentation. Tiffany didn't really show a HR diagram. The idea is that you can present the life of a star not in this kind of schematic diagram, but on the HR diagram, where you can point out on the HR diagram where the star would go, where our sun would go on the HR diagram. This text is fully detached from the figure. And usually the figure is the essence of science, not the text.
Okay, this chart is called the chart of nuclides, and as you can see, each dot in this chart represent an element, and the x-axis is the neutrons number of the elements, and the y-axis is the number of proton. And in these black dots, they are the stable nuclides, and for the gray dots, they are the radioactive and also the unstable nuclides. And because the black dots, they're kind of forming a thin kind of like band-like shape, so we call these black dots the band of stability. And also, an isotope means the atoms that have the same atomic number, but they have different neutrons. And also their mass number will be different. And isobar means the atoms that have different protons and neutrons, but they will have the same mass number. And alpha decay means an atom loses an alpha particle in results of losing 2 neutrons and losing 2 protons, which is probably the same of losing an helium elements. And in the graph, it would go down like this, just go downward and leftward. And beta decay means an atom loses a beta particle in results of getting a proton and loses a neutron. So in the graph, it would go up and go to the left like this. And after the beta decay, it will transform into the isobar of the nuclei. Okay, and an electron capture means an atom loses a proton and gets a neutron. So in the graph, it would go down and go to the right like this. And some atoms are stable or unstable depend on the ratio of the number of neutrons. We just use this and protons, we use this Z to represent. So when the protons number is smaller or equal to 20, the ratio of N to Z will be most stable if N to Z is equal to 1. And when the protons number between 21 to 40, N to Z ratio would be most stable at 1.25. And from 41 to 80, N to Z ratio would be most stable at 1.5. And if it is above 83, the most stable nuclei would not exist.
Can you explain that beta decay?
Beta decay means an atom loses a beta particle. So after it loses its beta particle, it would get a proton and lose a neutron. So in this graph, it says getting a proton, so you go up 1 and lose a neutron and move to the left. So it would go upward and go leftward. And after beta decay, the atom would transform into the isobar.
Oh, Henry, what is a beta particle? Because you say alpha particle is a helium atom, right? So how about beta particle?
An electron.
An electron. That's very nice. Can you maybe write on the blackboard what is beta decay? What's this? The left is neutron, and the right one is proton. Because neutron has no charge. So imagine that the neutron split into a proton and an electron.
Okay, I think you do good.
Okay, thank you.
I also think Henry did a good job. So thank you, Henry. Today we will start with the topic nucleosynthesis. Last week we talked about Big Bang and what happened right after the Big Bang. So you know there's a very famous scientist called Hawkins. He wrote a book called The First 3 Minutes. And in that book, he described what happened after the Big Bang. Of course, most of these was based on computer modeling. it is believed that temperature at that time was so high that no atoms existed, only fundamental particles, even smaller than neutrons and protons. There were no atoms or elements yet, right after the Big Bang. But then, for this lecture, we want to know how did the universe then pass from the state with only fundamental particles to the state where we know that we have elements, and later we know we have molecules. So that's what we want to know from cosmochemistry. The stellar synthesis theory provides solid scientific answers to this question. And again, I italicize solid here because this is what our textbook authors think. This is a very solid theory. Before we talk about stellar synthesis, I want to refresh your descriptive atomic physics. So in descriptive atomic physics, we have a planetary reality. The planetary means on planet. Atoms are neither created nor destroyed, except in nuclear reactions. And basically, most nuclear reactions are like artificial, like a nuclear power plants, nuclear bomb. These are artificial, but we know, of course, in nature, there are also radioactive decay. But the amount of new atoms created by this kind of natural radioactive decay are negligible. For most of the elements, they do not come from the planet. They come from stars. How were they formed? That's what we want to know in this lecture. And to do that, we need to refresh ourselves. The fundamental forces. We know we have strong field. I hope you still remember. You should remember better than I do. We have strong field, or strong force, weak force. And then we have electromagnetic field. We have gravity. We have these fundamental forces. Then we want to know what binds neutrons and protons together. This is lithium-7. We know in lithium-7, we have proton, we have neutron, and although all protons, they are positively charged, they can stick together, which is, of course, counterintuitive, because electromagnetic force tells us the same charge will oppose each other, and only things of opposite charges will stick together. But these are of the same charge. How can they stick together? The answer lies at strong force. Here, this diagram shows you the subnuclear particles, 次原子核的那个粒子, how they work. What we called proton and neutron, they are actually made of quark. I guess you heard of it. And then we have up quark, down quark. The so-called proton and neutron, they are actually different combination of up quark or down quark. Proton and neutron, they can be stick together by gluon. This is strong force. And the second fundamental force is the convertibility of proton and neutron. That was exactly what Axel and Henry together they wrote on the blackboard, which is also the beta decay. A neutron can be converted to proton and electron plus something else. That's what Axel said, but I think that's too detailed, so I won't talk about it. The reverse of this reaction, because here it says convertibility, which means P can be converted to N, and also N can be converted to P. The reverse reaction should also work. And the reverse reaction is exactly what was presented in Henry's assignment, electron capture. Here is the detailed mechanism of beta decay, where you see these horrible names like W boson, antineutrino, blah, blah, blah. I won't talk about this. The weak force refers to the convertibility of proton and neutron. So we now refresh ourselves regarding strong force and weak force. Now, here is a summary table regarding the 4 fundamental forces, where we see strong force acts in the atomic nucleus to bind protons and neutrons together, and weak force is also acting at the nuclear particles. It refers to the convertibility of P and N. We have another force which acts everywhere. The distance over which it operates is infinite. And then we have another force which is well beyond the atomic scale, large masses needed. I need to hear from you. What are these 2 forces? Henry,
Gravity.
which one?
Also maybe down.
Right, gravity. Victor,
Electric force.
electromagnetic force, 电磁力. 4 fundamental forces. We refresh you this because later when we talk about mechanisms, we need you to know the terms. Because later we will talk about processes, we will use the terms mentioned here. We need to talk about some energy consideration of nuclear fusion. For chemical reaction to take place, it actually only operates at electrons. You will have a very good understanding of what this sentence is about during the lecture of mineral chemistry. The reaction temperature is about like 10 to the 1st to 10 to the 3rd degrees Celsius. But for nuclear reaction, it's totally different. It needs to take place at the nuclear level, so the reaction temperature has to be higher than 10 to the 7th degrees Celsius. And temperature increases with velocity. Because this kind of temperature is difficult to produce in artificial environments. Here I want to ask a question. What is the highest temperature that can be generated in a lab, in a university lab? What do you know?
600 degrees Celsius.
How do you know that?
We dry the bottle.
Combust the bottle. So Hardy says 600 degree. You should be aware that if you use 600 degree for that device, the upper limit of that device must be higher than 600 degree. So actually, usually the maximum temperature that can be reached in a laboratory, in a university laboratory, is about 1,200. That's the maximum, almost. Okay, how is that? It's almost the temperature that's possible to melt quartz. Why is that? Because quartz is an often used material in lab. So that's the maximum we can get. And you see, for normal laboratory, it's no way that you can do this. It's far too hot. For laboratory which really need to work on nuclear reactions, they need to create a transient. Transient means short time, high temperature. And they can do this by increase the velocity of the particles. That's the reason artificial nuclear reaction can only be induced by explosion. This is out of control, so this is usually not considered, or particle accelerators. So that's the reason why advanced country, they want to build laboratories for particle accelerators, because only with this device, they can really simulate nuclear reactions. We need to talk about the energy consideration of nuclear fusion. 2 atoms, they have most of their mass is at the nucleus. The nucleus is, they are both positively charged. This one and also this one. And of course, there are electrons orbiting around the nucleus. You can imagine that if you force 2 nucleus to close together, there will be repulsive electrostatic force. That is one of the 4 fundamental forces, electromagnetic force, which will keep the nuclei apart under normal Earth conditions. However, if 2 nuclei can be brought close enough, for example, there is an exact number for that, 10 to the minus 15th meter, so a very small distance, then the strong force will suddenly kick in and stick them together. But there is one very important proviso. That's it. It has to meet this proviso. E is equal to mc squared That means if these two nuclei, they are brought together, and then after they are fused together, there is a loss of mass. Then energy is released. That usually means the reaction is spontaneous. 自发性的, spontaneous. In contrast, if there is a gain in mass, energy needs to be added in to make the reaction happen. That means this reaction is unlikely to be spontaneous. You need to put energy into the system to make it happen. That's for descriptive atomic physics. I hope it's simple enough. So now let's go to chart of nuclei. That is your assignment, so I will keep it short. The reason that this chart of nuclei deserve an assignment is, I don't know if any of you know that, the chart of nuclei itself is a Nobel Prize. Some scientists figure out the whole system of atom plus nuclei in the whole universe. Then they provide a systematic view how they should be. Before this, I want to ask you, what's this? We have sulfur 32.
isotope
I mean, what does the number exactly mean?
原子量，原子量。
Atomic mass. What does atomic mass refer to?
Refer to the number of neutron and the number of proton.
Mass number n plus p, proton number p. I hoped after this class, I don't know how many of you will use isotope. However, some of you, I hope, probably will stay here for our graduate school. At the graduate school seminar, sometimes I saw that some students, after taking this course, he or she wrote isotope like this. And when I see this, and when I know that this student has taken my course, I was, oh my God, I'm so embarrassed. It means C to the 12th, 碳的12次方. I hope this will not happen. Sulfur 32 and sulfur 34 are?
Oh, isotope.
So what would be isobar? These are isobar. So isobars simply have different letter here. So why should you care about isobars? Will you ever need to use isobar? We know we use isotope a lot, but why should we know this?
For beta decay and electron capture.
That's very good. That's a theoretical consideration. But there is another practical consideration that would really bother chemists. Because right now we just talk about principles. However, in the future, if any of you really go to a lab which really measure isotope, you need to know that the instrument, they only look at the mass. They don't really look at the letter here. The instrument, they only recognize mass. For example, today you want to measure CO2. Can any of you tell me what is the mass of CO2? If you consider the most abundant isotope, carbon-12, oxygen-616, what is the mass?
44.
Very good. Can any of you think of anything that has the same mass? Yes, it's easy to have some other molecules to have the same mass. So if you don't have the concept of isobar, you are easily misled by instrument. The instrument will lie to you. You say, I think you are measuring CO2. No, I measure 44. I don't know what is CO2. So you have to be careful with that. Chart of nuclide is discussing the assignment, so I will pass this very quickly. So we talk about isotope, isobars, beta decay in this direction, electron capture, which is the reverse reaction of beta decay. We also talk about the NP relationship, like when the proton number is small, you can see that the band of stability tend to stay around the 1-to-1 line. This is the one-to-one line. However, when the proton number is higher than 20, you can see that in the nucleus, we need more neutron to stabilize. These two lines, the band of stability and this one-to-one line, they are further away from each other with larger proton number, which means the more proton you have in the nucleus, the more neutron you will need to stabilize. Otherwise, the proton is like, I hate you, I hate you. So they want to split. So that's the reason why at the end, we no longer have stable isotope here, because it's simply too unstable to have stable isotopes. Here, Henry already talked about this kind of different decays, but right now, I will show you a few more with some specific cases, like a beta decay. We will talk about this process is actually radiocarbon dating, the technique of radiocarbon dating. Radiocarbon will decay to nitrogen-14 following beta decay. And in other words, you can imagine that the production of radiocarbon is by electron capture, so the reverse of beta decay. And for electron capture, there is another dating technique called potassium-argon dating. In this class, we will also talk about this technique only very shortly. This method is basically used to date volcanic rock, 主要是火成岩的定年. So we will talk about this. And there's another important information that you should know, that in seawater, we have also natural radioactivity, because recently we know that Japan is releasing treated water. So like the whole government is so concerned about this treated water, 川水. Some crew or captain of our research vessel, 就是研究船的船员, they are also concerned, because you know that in very long multi-day research cruise, like maybe more than 1 week, the fresh water on research vessel is actually produced by seawater. So these sailors, they are very concerned, will I drink treated water or whatever? What you should know is the majority of radioactivity in seawater comes from this. This is the major source of radioactivity in seawater. Okay, under natural condition. Why? Because this is very abundant in rock. So it's delivered to the ocean by weathering and river discharge. Lastly, alpha decay, we will also talk about this in the lecture of uranium disequilibrium, 右系不平衡. We will use this. So we will use these 3 different kinds of dating technique. We'll talk about them. And here, there is a process called spontaneous fission. You might think, okay, this has nothing to do with us because it has no stable isotope. But in fact, there is another dating technique related to spontaneous fission. It's very widely used in geoscience department. I think in this lecture, we won't talk about this. And if you zoom in, I think some of you probably noticed that this is not a smooth line. It's actually, there's zigzag. And if you look closer, you will see that it's a little bit like a stepwise. I don't know the reason for this, but based on observation, you can tell that elements with even numbers of protons have more stable isotope than those with odd numbers of protons. It's just an observation. So right now, I need to ask an important question. How do you know what are the all possible isotopes of carbon? How do you know that? How do you learn the full spectra of isotope? Like you want to know the isotope of the whole row here. Furthermore, you probably also want to know whether if it's a radioactive isotope, how do you know if it undergoes alpha decay or beta decay or something else? How do you know that? The answer is incredibly easy.
Just by observing the decay.
So you are answering from the perspective of a nuclear scientist, but my question is actually much easier. How do you collect the knowledge? If you open your web browser, which keywords do you need to use to find the isotope of something? All you need to do is That's all you need to do. In Wikipedia, it has this information page for every element. Here, you will see, in fact, for carbon, it has isotope ranging from carbon 8 all the way to carbon 23. And it will also tell you what kind of decay does it undergo. Here, it will print the major isotope and their mode of decay. So in this way, if today you want to measure, you will know which instrument you should look for, because alpha, beta, electron capture, they all need different kinds of instruments to measure them. And of course, you can look for isotope of hydrogen. Right now, we have tritium water, which is made of hydrogen 3. What is its half-life? It's 12.32 years. So it will affect you, us. We will talk more about this later. How do you know how long it will affect you? Its mode of decay is beta decay. If you need to measure it, you need to look for beta counter. Nucleosynthesis. So after the Big Bang, there is actually also nucleosynthesis. In literature, you will hear a very specific name called primordial. Primordial means primary, the most fundamental, primary. Nucleosynthesis, that usually means the nucleosynthesis right after Big Bang. This is based on the knowledge of distribution of stable isotope and computer model. So we don't have proof for that. And the original form of matter based on scientists is neutron. Free neutron is not stable. Free neutron only have a half-life of 10 minutes. Then it will undergo beta decay every 10 minutes. Right after Big Bang, it is believed that the following atoms or nuclei were produced. That is 71% of hydrogen 1, 0.01% of hydrogen 2, and then trace amount of helium 3 and 29% of helium 4, and then trace amount of lithium, beryllium, and boron. That's all we have after Big Bang. We will talk further later in these courses. We will talk about helium 3 because helium 3 is a hydrothermal indicator. We will also here briefly talk about helium 4 because this is a carrier gas for model instrument. I don't know in Professor Louis' lab, but if you want to join Yongbin's lab, I mean Steve, then you will definitely see some helium cylinder, 一些氦气的气瓶. Helium 4, that's the regular helium you can find on Earth. It's a very rare resource, very rare. I can recall that during my career, since I was a graduate student, I have heard about helium crisis, 氦气危机 for many times. It's usually related to Russia because Russia is currently the major producer of helium gas. Helium gas is usually produced in old continental crust. 它通常是在很老的火成岩的地盾里面会生产 because the production of helium-4 is related to volcanic rock. Last year, we have this conflict between Russia and Ukraine. Do you know how much helium-4, its price has changed since then? Before the crisis, each cylinder will cost us 6,000 to 7,000 new Taiwan dollar, NTD, 6,000到7,000块. Do you know how much is it now? The price has doubled. So it's now 15,000, 16,000. So it's incredibly expensive, and furthermore, helium is not a renewable resource in regular laboratory operations. So it's like we are consuming, and then the production by rock, its production rate doesn't really catch up our consumption rate because many instruments need helium. So I don't know, maybe in the future when you grow up, the helium will be triple the price. Although actually in the universe, it's actually the second most abundant component. But on Earth, it's a rare resource, very rare. Here are the stable nuclides. So pay attention. These are only the stable nuclides believed to be produced during primordial nucleosynthesis. These are the isobaric line. Mass 5 and mass 8, they are missing. Why? Because for these two mass, they are only radioactive isotope. Only radioactive. So you don't see this mass. There might have been other radioactive nuclides, however, their half-lives are too short for them to serve as the parent nuclides for new elements. Now we talk about element formation in stars. Then we need to review the HR diagram. This is a historical review. In 1905, a Danish astronomer and independently an American astronomer, they noticed that the luminosity of stars decreased with spectral type O to N. And then they developed the technique of plotting absolute magnitude of a star versus its spectral type to look for families of stellar type. Take a look. Here it says spectral class. It's actually the spectral type here. However, if you look closer, it also says surface temperature. In my assignments, that's how I wrote my question. So the x-axis is surface temperature. How do you know it's related to surface temperature? In fact, originally, it's not really based on surface temperature. It's based on spectral class. It is later that scientists realized that the spectral class is related to surface temperature. And then the y-axis is luminosity. As Axel answered during our discussion, it's related to brightness and distance of a star relative to us. Okay, so now we have a detailed explanation of the x-axis and the y-axis. The y-axis, the luminosity, let's see if it's here. Okay, right. Absolute magnitude. So it's actually the intensity of starlight. It's a proxy for celestial objects' intrinsic brightness that would reflect inner temperature. It's defined as the intensity that can be measured at 10 parsec or 33 light years away from the observer. So we have to normalize the distance of the star to the same distance. So we use 33 light years. And then the sun is set as the reference. So you can see the one here. It is the sun. Spectral type, it actually refers to the composition of starlight. This is the spectral type. So this is actually based on the color you see from a star. Okay, you know some star looks reddish, some look blue, some look white, some look yellow. So they have different spectral light type. That means their color. It's a proxy of a star's surface temperature. I don't know if this rings a bell. Surface temperature. Classification of star based on their spectral characteristic, that usually means color like this. So for star lovers, they have a phrase like "Oh, be a fine guy, kiss me," to remember this. But in fact, they are this. They are Fraunhofer spectrum that you have learned last week. Different color you see, be a fine guy, kiss me. They actually refer to spectra of different intensity of dark bands. Okay, and these are the exemplary stars. So the relative abundance of ions varies with temperature, and therefore it's a proxy of surface temperature of stars. And then in my assignment, there is another important question. How do you know the size of the star? So I don't know any of you have figured out that this low. So I will see that after reading your assignments. This is the Stephan-Boltzmann law. L is the luminosity of the star. It is related to its radius, its surface temperature, and the Stephan-Boltzmann constant. Here are questions for you. Therefore, for stars of the same temperature, bigger stars will be
more lighter.
lighter, exactly. For star of the same luminosity, the temperature, bigger star will be
Lower.
lower in what?
Surface temperature?
Both answers are correct. So now, I need a student to tell me. So now we have temperature and we have luminosity. And here, they also say, like same temperature, what will happen, same luminosity, what will happen. So here, I have a line here. If here I have a star with this size, what will happen for the star in this direction or for the star in this direction? For stars of the same temperature, bigger star will be lighter. Smaller star will be darker. Okay, very good. Now I have a same luminosity. Same luminosity, bigger star will be, and smaller star will be. Very good. Now you see how they figure out the size based on the Stephan-Boltzmann law. Here, the axis is reversed. Here we have low temperature, reddish star, and high temperature, blue star. And luminosity is in the normal scale. But usually, if really look at some literature, they actually won't tell you any size. So this is a cartoon style figure for people to easier understand. But in reality, it's more like this, okay, just stars. Main sequence star. They represent 90% of observable stars like this. Most of the stars are here. They are the so-called main sequence, and they have different sizes according to what we draw on the blackboard. In this case, larger ones are hotter, and our sun is not big. Take a look where it is. Sun is here. So you see it's really not big. Then we have red giant. You must have heard of it as a school student. It has large, bright, but cold on the surface. Is red giant. And then we have white dwarf, which is extraordinary small and dim. So this one is easier to see. We have giants here. It's at the upper right of the main sequence. And then we have the dwarf here, which is at the lower left of the main sequence. What we haven't really discussed well is how would the star evolve on the HR diagram? Will it go this way, this way, this way, this way? How would it go?
太阳的话，那它就算是smaller star，it will gradually cool down and stop glowing, and it
Poor
will
guy.
go through the planetary nebula phase.
There's an important phase missing for our sun.
会先变红巨星还是什么？
It will be a red giant first. The sun will go here and then go here. And why? Why it will become a red giant and then it will turn into a planetary nebula and then later it will turn into a white dwarf?
Because of the star is burning is on fuel on the center, so the gravity is not pulling as much the star together. So it's beginning expanding until the giant. I think I can kind of figure it out, but I don't know why. Then it's just crushing itself like planet nebula, then white dwarf. That I don't know, but I think that it's becoming a giant because of lack of fuel, and then so deficit in matter that doesn't pull the star together with the gravity.
Basically correct. Because the sun, as it is now, or as a giant, its mass doesn't really change that much. It doesn't mean that when it becomes a giant, it has gained extra mass. This doesn't happen. Of course, when it becomes a giant, it will probably eat us, the Earth, but this Earth is just very small compared to its real mass. Then why can it become so big? Because at that time, something happened, and then the sun's gravity is not sufficient to grab things around it. That's the reason it will expand. Then you might ask what really happened. We will talk about this next week. Please explain figure 3-7 and 3-8. This is the so-called R process pathway. And this is a segment of the chart of nuclide. You need to explain all these arrows, not individual one, but what the thick arrow means, what the thin arrow mean, the open square, solid square, dashed line square. What does that mean? And of course, you need to answer these questions. First, what is R process? Where does R process take place in the universe? And what is S process? And this is the S process. And again, you need to explain the arrow, the box. Again, where does S process take place in the universe? Where to find the respective nuclides on the chart of nuclides? If you understand these processes correctly, you will know on the chart of nuclides, there's a tendency for the R process produced nuclides to spot. And there is also a place where you can find S process produced nuclides.